Good day, everyone. I am Reann Janelle Cuizon, and welcome to Zooming into Science. Today, I am excited to walk you through the fascinating world of microscopy towards the application of X-ray fluorescence microscopy with synchrotron radiation, a study by Radiation Physics and Chemistry 2024. But first, what is microscopy? Microscopy is essential for studying the structure and composition of materials at a microscopic level. Electron and optical microscopy have their limitations. That's where X-ray fluorescence microscopy comes in. Now, what is fluorescence microscopy? This works by exciting molecules with light. When the photon hits a molecule, it absorbs the energy, jumps to a higher energy state, and then emits light at a longer wavelength when it relaxes. This is called the Stokes shift, the basis of fluorescence. The emitted light is then used to map molecular structures and interactions. Ground state is where the molecule starts in its lowest energy state. Absorption: a photon excites the molecule from the ground state to an excited state by absorbing light of a specific wavelength. Non-radiative transition: some energy is lost as heat through internal conversion and vibrational relaxation, lowering the energy within the excited state. Whereas the fluorescence emission, the molecule returns to the ground state, emitting light at a longer wavelength. The key principle of fluorescence follows Stokes shift, meaning emitted light is always red-shifted compared to absorbed light. Microscopy has always been a crucial part of scientific research. Techniques like electron and optical microscopy are great for imaging, but they have limitations in chemical sensitivity and depth penetration. XFM, on the other hand, combines high resolution and chemical sensitivity. By using focused X-rays, it excites atoms in a sample, causing them to emit fluorescent X-rays. These emissions are then analyzed to map the distribution of elements at the nanoscale, something that traditional methods struggle to achieve. But how does X-ray fluorescence microscopy works? First, a focused X-ray beam excites the atoms in a sample. The atoms emit fluorescent X-rays unique to each element. Then lastly, the emissions are recorded and maps out the distribution of the elements. Since XFM is non-disruptive, it has high resolution, around 60 to 110 nanometer, and can penetrate deep into samples, making it ideal for complex material analysis. And then the applications are biomedical research, material science, and environmental science for mapping. Fluorescence microscopy also maps molecular structures but works differently. It relies on the absorption and emission of light by fluorophores. While fluorescence microscopy shows molecular interactions and movement, XFM provides high-resolution chemical composition maps. Combined, they give a more complete understanding of biological and material systems. In the aspect of genetic mutation, microscopy analysis reveals structural variations at different magnifications, highlighting distinct morphological features and surface characteristics. In scanning and data collection, the samples are scanned horizontally in continuous mode. Second one is the X-ray fluorescence spectra is recorded with the silicon drift detector. The data is being analyzed with PYMCA software to create the 2D structure. Then lastly, RGB overlays for visualization. From the given research, we could see the table 1 of data. For macroalgae, XFM revealed nutrient storage and photosynthesis, while in dental tissue, XFM showed diet and environmental markers. Third one, geopolymer, XFM linked arsenic and iron to mineral formation. And lastly, coatings, which contains high voltage coating, improve emexine dispersion. Before wrapping up the study, here is the critic of the study. First, with the strength, high resolution elemental mapping at the nanoscale, detects multiple elements simultaneously, broad applications in material science and biomedicine. The last one provides both chemical and structural insights. For the limitations of the study, first, motor misalignment causes dial mismatch. It requires specialized facilities. Third one, complex data analysis. And then lastly, it may be sensitive to sample conditions. In conclusion, XFM is transforming scientific research by providing detailed insights into material composition and structure. Its applications in biological and material science are driving innovations in drug delivery, biomaterials, and sustainable manufacturing. With its growing adoption, XFM will continue to push the boundaries of scientific discovery. That's all for now, and thank you for listening.